All right, so this is our second day of working with work and force. Be sure to be looking at the calendar for the homework problems from the textbook. Keep in mind you can set those up, just set up the integral and then actually evaluate the integral on your calculator when you're doing it. The homework problems from last night are posted. We'll pause for 1 minute to allow you to check your answers. All right, so we'll fly through each of these in case you had questions. First ones were all going the same distance, so it's just a force times the distance. 100 times 10 for the first one for 1,000 foot-pounds. 2,800 times 4 for 11,200 foot-pounds. In 3, we were working with metric, so we had 112 times 4. You could either say Newton meters or joules for that 448. 4 had the most work you had to do. You had to take 5,280 feet, which are in a mile, and divide it by 2 because you're going a half mile. There's 2,000 pounds in each ton. So 9 times 2,000 gave you 18,000 pounds. And now you could do your force times your distance to get your foot pounds, that 47,520,000 number. In 21, we want to do the volume of a slice. So we start with our density of the water, the 62.4 pounds per feet cubed. Then your slice of each slice of water was 4 feet by 5 feet times a little bit of thickness, which I call dy. So that gives us a feet cubed. Then you have to multiply it by the distance it traveled. Your top was 4 minus a random y value, so 4 minus y for your distance. We were only emptying half of it, so the top half is what would get emptied, so that's why it went from 2 to 4. The only thing that changed in part B was we were emptying the whole thing, so it went from 0 to 4. Now I showed the by hand doing that. You could just evaluate that in your calculator after you set up the integral. In 31, our chain weighs 3 pounds per foot times x, the distance that it would travel. That turns it into a pounds. Now, dx represents each little bit that it is lifted. So that's our force times our distance for the work. We want to wind up the entire chain. So go doing all the little slices of chain from 0 to 15, and we get that 337.5 foot-pounds. In 32, we were only winding up 1/3 of the chain. So of the 15-foot chain, we're going to wind up 5 feet of it. It is the top third of the chain that is getting wound up. So that part's getting wound up. So the bottommost part that gets to the top is traveling 5 feet. The topmost is going 0 feet. Well, now this is 10 feet that's left over. That entire 10 feet, all of it moves the same amount. It all moves 5 feet. So first, find the weight of that section of chain, the 3 pounds per foot times the 10 feet, and then the distance is that 5 there, because every single link of chain you can think of it as moved 5 feet. Whereas in that top 5, they all move different amounts. That's why we had to do the integral. And then 33 was pretty similar. We had 3 pounds per foot again, so the 3x dx. We want to run the winch until the bottom of the chain is at the 10-foot level. Well, it started at ground level, so that means if we were here, so this 10 feet got wound up, so that's why it's 0 to 10. But then there was 5 feet that never made it to the top, so we do the 3 times the 5 to give us an amount of pounds, and then that bottom 5 feet of chain, it all moved up 10 feet together. So that's why it's just times 10 there, so you eventually get 300 foot-pounds. In 34, we wound up the entire chain, so the integral is 0 to 15, but then there was a bunch of stuff on the end. It was 500 pounds, and it all traveled 15 feet. So some things from yesterday. Work is equal to force times distance. When you're finding work done by pumps, the force, you want to think the volume of a slice times the density. So for work, you're doing the volume of the slice times density times the distance traveled, and then we're sticking that in an integral. So in our packets, we want to go, oops, we already did those ones. We want to go to question 1, where it talks about a spherical water tower. And we've got that pictured here. We've got a radius of 10, and it's on supports, so the tank is 40 feet above the ground. Water is pumped into the tank from the ground level. Find the work done filling the tank up to a depth of 8 feet. But when you have anything circular facing us like this, it's good to draw your axis so it's at the center of the sphere. So this is really at positive 10, this is at negative 10, and our ground level here, because it's 40 feet below the sphere, this is really at negative 50 in terms of our axis. Well, we want to think of a random slice of water. So I'm going to randomly draw in a slice of water there. So let's start with our density of water, 62.4 pounds per feet cubed. Well, we want to turn that into a force, which is just a pounds. So we need to multiply that by a feet cubed, which is a volume. We always multiply by the volume of a slice. If we're doing that horizontal green slice of the sphere, our slice should be a circle with a little bit of thickness. That little bit of thickness will just be a dy. And then we're basically going to find the area of that circle. Well, to find the area of that circle, we need to find this radius. So let's set up a right triangle. This would be a y, this would be an x, and this hypotenuse is 10 because the radius of the sphere was 10. And this is the reason we like to draw our axis centered at the middle of that sphere. It just makes the Pythagorean theorem easier. So we're going to have x squared plus y squared equals 100. Now the thing we want is that x, because that's the radius of our slice. So we're going to end up having x is equal to square root of 100 minus y squared. Technically it's plus minus, but you can pick one of the two sides. We'll pick the right side, so it's the positive side. So our volume of our slice will be a circle times a little thickness. So pi times our radius, which we just identified with square root of 100 minus y squared, because it's radius squared, times the thickness, which is dy. Well, this wipes out the feet cubed, so this is now pounds, which is our force. So that's great. We just now need to figure out what is the distance that each slice traveled. Well, this particular slice is traveling that distance. So for that, we're just going to do a top minus a bottom. So our top is some random y value minus our bottom, which is negative 50. So minus a minus just becomes a plus. So really our distance is y plus 50. So this is what's going to go in our integral. Any constants can go out front. So we'll put the 62.4 pi out front. When we square the square root, we're just going to have 100 minus y squared now. We'll have the y plus 50, and we'll have the dy on the end. Now your integral values are always the different locations of the slices. So our slices of water needed to take place in the sphere. So the lowest that a slice could be is negative 10. And if we want to go to a depth of 8 feet, really for us, 8 feet would be when we're at our y value of negative 2. Because negative 10 to negative 2 would be 8 feet. So the top would be negative 2. And that would produce a depth of 8 feet when we fill it. So from there, we can just punch the integral in our calculator. So we'll pause the video for 1 minute for you to be able to do that. So we should have either gotten that in fraction form, or that's 1320550.4 pi, and that's foot-pounds. And if you put the pi in, it would be whatever that times pi is. In part B, we want to fill it to capacity. So our density is the same. The volume of a slice is the same. We're still coming from the ground up to a random y value. So distance is all the same. The only thing that's going to change in this one is our bounds. So we'll go -10 to 10. So in your calculators, you can just scroll up and select the previous one. Change the bound on top to get our new amount of work it takes to fill the whole thing. In terms of pi, we should get 416 and 4 zeros pi foot-pounds. So we did the density times the volume of a slice times the distance it traveled, and then our integral bounds were where the slices of that liquid could be located. All right, moving to 2. We have a 10-foot long trough, has an end cap shaped like an isosceles trapezoid as shown in the figure. Find the work done in pumping the water out through a 2-foot pipe attached to the top of the trough. And you see that we've got the end cap view on the bottom and then the angled view on top. So we're going to start with our density, 62.4 pounds per feet cubed. We want to turn that into a pounds, so we need to multiply it by the volume of a slice. Well, each of our slices here are going to be rectangles. It's going to be whatever that green dotted line is times 10. And then we'll multiply it by a little bit of thickness to turn it into a volume. Well, we know that bottom base is 4. We've got to represent the little bit extra on each of those. So let's turn this into an isosceles triangle. Or sorry, not an isosceles triangle, a right triangle. And let's say we called this H and we called this X. Well, we need to somehow represent that length X, and that would also have the same amount over on this side. Whatever we get X to be, we'll add those twice to 4, and that will represent that green length. Well, what we can do is we can set up similar triangles. Notice the top is really 6, which would make each of these be 1. We know the vertical for the whole thing is 3. So what we know is that in the big triangle, it's 1 relates to X in the small triangle. 3 in the big triangle relates to H in the small triangle. If we cross multiply, H is equal to 3X, or in other words, X is equal to 1/3 H. So if these are each 1/3 H, the whole green horizontal line can be represented as 2/3 H plus 4. Times the 10. That gives us an area of a rectangle times a little bit of thickness. Well, based on our variables, I called our vertical there H, so our thickness would be a little bit of change in that, which would be dH, and that now turns us into a pounds, which is a force. We now need to multiply by the distance that each slice would have to travel. Well, this time the slices are being pumped out through the pipe on the top. So that is the distance that this slice needs to travel. In terms of our whole scenario, this whole height is 5. So this yellow length would be 5 minus some random h. So 5 minus h would end up being our distance that each slice travels to get out the top. And you can always just spot check your distances. Like if that green dotted line was at 1, you can just think about it. Oh yeah, it should take 4 to get out the top. 5 minus 1 is 4. Okay, that seems to check out. So from there, we'll do our integral. Any constants can go out front. 10 times the 62.4 just gives us 624. We'll have integral of 2/3 h plus 4 times 5 minus h dh. Our trough is filled to a depth of 2 feet. So we need to think about where could the slices of water be located. The lowest slice would be at 0. The highest slice would be at 2. And we're going to pause the video for 2 minutes for you to get your answer to this one, and then also see if you can make an adjustment in your integral to find your answer for B. So for part A, we should have 69056 over 3 foot-pounds. And the only thing that changed in the second is we're now going 0 to 3. Because remember, the trough only went to a height of 3. The extra 2 was where it had to travel through the pipe. So for that one, we should get 31,824 foot-pounds. We'll look at one more example. Going over to number 3, we now have a cone. It's pointing downward. We've got a radius of 4 feet and a height of 12 feet. And we're going to draw in our axis so the origin is at the point of the cone. So this is 12. That's 4. The pipe is 2 feet, so the end of the pipe would be represented by -2. And we're pumping in from the bottom in this first one. And we want to fill it with oil till it's 10 feet deep. Well, oil's density is different, so we have 50 pounds per feet cubed. We've got to multiply by the volume of a slice. So a random slice would look like that. The reason we always slice it horizontal again is because that slice will all move the same distance together. If you sliced vertical, the oil in that slice would move different distances. That slice is going to be a circle with a little bit of thickness. So we have to figure out what this length that I'm going to call x is. And we'll do that by using similar triangles. We'll call that y. And then think of the big triangle as being the whole cone. So 4 in the big cone relates to x in the small triangle. 12 in the big relates to y. So that would be 12x equals 4y. Or x equals 1/3 y. So we're going to have a circle times a little bit of thickness. So we'll have pi times our radius, which was the x, which we said was 1/3 y, squared. So that's a circle. And then our little bit of thickness, which is dy. And then we've got to do the distance that it traveled. Well, our distance, it was pumping in from the pipe to our random slice. So if we do a top minus a bottom, that'll be y minus -2. That'll be a plus. So we'd really have y plus 2 for our distance. So if we squared the 1/3 and the y, we would have 1/9 that we could pull out front along with a pi. So we're going to have 50/9 pi out front. Again, the 9 in the bottom came from squaring the 1/3 and then the pi pulled out. We would have a y squared left that we had gotten from the radius squared. Y plus 2 and then dy. We wanted our oil to a depth of 10 feet, so our slices of oil could occur from 0 to 10. And we'll pause for a minute, see if you can get this, we'll say in terms of pi again, for our work. And make sure to stick units on your answer. So we should have 475,000 over 27 pi foot-pounds. So in part B, the tank is full now. So one thing that'll change is our bounds and our integral, because the tank really had a full depth of 12 feet. So that's going to be 0 to 12 now. And we want to find the work pumping the oil out the top of the tank through a hole in the top of the tank. So the other thing that's going to change is our distance. So slices didn't change at all, but we've got to change from the first part, we got to change those bounds and we got to change this distance. So our integral now is going to be 0 to 12. We'll still have the 59th pi and the y squared. We've got to figure out our distance and then dy. So now our distance is going to be from the top to our slice, because we want to pump it out a hole in the top. So our top is at 12 minus some random y value where our slice was. So 12 minus y will be our distance. And if we were to punch that in the calculator, we'd get 9,600 pi foot-pounds. So that's it for this video. With the time left in the period, you can work on your homework. There are textbooks over on the bookshelf. Help yourself to them. Just make sure you put them back when you are done. Have a great rest of your day.